Adam Savage here in my cave with my friend Kipp Bradford. How are you, sir?
Good, and you?
Very good. I'm excited because we are about to explore a new vista of cosplay technology. Now, if you're a regular follower, you know that I built myself a spacesuit from Alien, a John Hurt's suit, and I wore it on the Comic-Con floor in San Diego in 2012? 2014. In 2014, and I almost got heat stroke wearing basically what was a quilt with armor attached to it. So the very following year, Chris Hadfield and I walked the floor in a pair of 2001 spacesuits, the silver Clavius suits, into which I built an integral cooling system comprised of a bucket of ice water with a recirculating pump and cool shirts. And that worked pretty well. But Kipp, among many other things that he has done in his life as an engineer, happens to specialize in extremely tiny refrigeration units. And we're hoping to build one here in the cave today, small enough for me to use in cosplay. So get ready, we're gonna get cold. All right, Kipp. Where do we start? There's a lot of little bits and bobs around the shop. I'm not even sure I know what this is.
Yeah.
Okay, so where do we begin?
Adam, this is a compressor.
Okay. Oh, this is the step that does Boyle's law that brings refrigeration and recirculates this stuff.
Yep.
Our gas that, so what is it? You compress it, when you release it from compression, the temperature lowers.
Correct.
And you get the refrigeration.
That's exactly it. So the compressor works just like any compressor does. There's a piston inside here, and in this case, the piston's a rotary piston, so it spins around.
Oh.
And as it does so...
Is it a vane pump?
It is a vane pump.
Oh, okay.
It is a vane pump. It sucks a gas into this inlet, pulls it through the compressor, and increases the pressure. Just like Boyle's law, PV equals nRT, as you increase that pressure, the heat also, temperature goes up because we're doing mechanical work. We put electricity in here. That electricity is what's doing that pumping.
Right.
Magnetic field turns the rotor turns the vane squeezes the gas. We're doing work on the gas.
Right.
So just like if you're pushing down on a bicycle pump,
it can get hot.
It gets hot as you're doing that work. So
right.
the energy from your arms is transmitted into the pressure of that gas. So gas gets hot. As we do work to it and it gets compressed, we can push that hot gas through another heat exchanger where we blow air over it and take that heat away.
And when we take the heat away, we're not just removing heat, we're actually compressing the gas as well? Or
no, we're actually just removing the heat.
Oh, okay.
So the pressure from this output side stays constant. The temperature is what changes. So we take that constant pressure gas, we blow the air over it, and the reason why the pressure doesn't change is because even if we take all of that heat away, the gas itself there's more new gas coming in from the back end. So what happens is, not that it changes pressure, but it changes state. We go from gas to liquid.
I see. So because we're taking temperature out, we can fit more gas in the same volume.
We can fit more gas in the same volume.
Okay.
That converts to a liquid, and that liquid then goes to the other half of the system where we boil it off.
And boiling it off is how we lower the temperature.
Exactly.
See, I know how a refrigerator works. I've logged that in my time, just a little bit.
It's if you're an engineer, you'll know this as a reverse Rankine cycle, which is a thermodynamic cycle that's fully closed loop, and we do work with a piston or a rotor or some kind of machinery that does that compression. So we're putting mechanical work into the system. And we go from electricity to mechanical work to thermal, and then we get rid of the thermal, and then we reverse and come back on the cold side, boil off, turn to a gas, and then we suck gas back in the inlet.
And it strikes me that this is an especially tiny compressor. Am I right?
This is.
Is this one of the tiniest ones?
This is one of the tiniest compressors, and this has a pretty fascinating story. During the first Gulf War, DARPA put out a call for man-portable, wearable environmental control systems.
Oh, for just the exact thing we're working on. And they did an RFP for tiny compressors?
Yes, and two companies won that RFP, and one of those companies is Aspen Compressor in Marlborough, Massachusetts. These are made in Kentucky. The designer of the compressor is a fascinating MIT mechanical engineering PhD.
Of course.
Of course. Who makes these incredibly well-balanced, super small, high-efficiency compact compressors.
And when you say well-balanced, that means that the compressor is efficient because it's not losing any of its energy to vibration.
Yes.
So when it's highly balanced, you have a smooth system and all the energy is going where you want it to.
Exactly. And it means that if you're wearing it, you're not going to get all of that vibration onto your back. It's not going to make a ton of noise. If you ever have your shop compressor turn on in the middle of the night and you hear that,
no, I have to put a timer on it because it wakes my neighbors up here.
Exactly.
Yeah.
Exactly.
No, normals live upstairs, and sometimes we make their lives worse. I don't know. They've never complained about the kind of music I listen to, so we'll see.
They're pretty cool then. So the part of the story about...
Wait, that was almost an insult, but I'll take that. It's just chicks whining about the ocean. That's my favorite music. Okay.
So the great thing about the DARPA story is that DARPA puts this call out, and they get a couple companies that respond to it with these super compact compressor technologies, and they quickly realize that putting people in spacesuits in the middle of the desert trying to fight a war is a bad idea.
Right.
Because
if you have any kind of system failure, they're super compromised right away.
Immediately compromised. But we get this cool technology out of it and this notion that we can make very compact refrigeration and cooling systems using a portable low voltage DC compressor technology. So the original purpose of this being fighting wars with people in these crazy suits, not the smartest idea. The result has been, I think, fairly transformative for a lot of medical applications. I use these for a medevac system that could stabilize people's temperatures in medevac helicopters after traumatic injuries.
On their way to a hospital.
On their way to a hospital.
Normally nothing substantive is getting done. You can actually bring their temperatures down. Wow.
So found some other uses for it, made some fun projects, and the last system I built was the world's second smallest wearable air conditioner.
Nice.
Couldn't quite get it to be the smallest because just got it to be the second smallest.
Okay.
And that is currently in a NASA spacesuit simulator that's running around somewhere in the world, pretending to be a Mars simulation spacesuit.
Kind of like what the guys are wearing on high seas experiments?
It was the high seas spacesuit.
Oh, fabulous,
so
fabulous.
The thing we're going to build is a replica of the high seas spacesuit air conditioner.
Oh my God, that's really exciting. One, I follow the high seas experimentation project for years, obviously. I revere what those guys have put themselves through, and I know the complications of that program, but also I love those suits.
They're great. Yeah.
I love reading about how much they love their suits, like they fall in love with them. Okay, so what is obviously this is the centerpiece of this, but how do we start to make our assembly here?
So this is our centerpiece, and there are two other pieces that we need. We need a heat exchanger to reject the heat, and we need another heat exchanger to absorb heat. One of those heat exchangers that's rejecting the heat is going to go from refrigerant, which is a gas in this case, to air.
Okay.
And we'll have a fan blowing air over that. The second heat exchanger will go from liquid refrigerant as it's vaporizing to cool water. And that water will then circulate through your cool shirt.
Ah, okay, right. So there'll be a heat exchanger between So we'll need like a big aluminum plate that's touching the water or something like that?
Something like that. We'll actually use a stainless steel heat exchanger that will go directly from the boiling refrigerant into the water.
Oh, okay.
And we'll tune the system a little bit so that the water doesn't freeze, or you could also use alcohol instead of water. And
great, I have plenty of that.
Even colder.
Yes, let's do alcohol.
So let's do alcohol.
I love that idea. Isopropyl, will that work?
Isopropyl works. I actually tend to use ethyl alcohol.
What's
vodka.
That? Vodka,
yeah.
great.
Yeah.
We'll send out for
ethanol.
Cheap vodka is plentiful in the Mission District.
And the reason why vodka is great is because it's non-toxic depending on how much you drink.
Since I don't drink, that's fine.
So you're all set there.
So shall we gather the parts over here?
Yeah, let's gather the parts.
Okay.
All right.
These are both versions of the same thing?
These are two versions of the same thing. And we have a big heat exchanger and then a smaller heat exchanger. Now, the High Seas project uses this smaller heat exchanger. And the High Seas project is not so noise sensitive. We can have a little bit more noise generated and it doesn't cause a problem. For you, though, I think we want to go with a bigger heat exchanger and a quieter fan. So
the weight is not much different.
No, they're both
fairly negligible. So sure, yeah, I can accommodate something this large in there.
And then we're also going to take two other heat exchangers over the table, and we'll talk about these two as well because they're pretty neat technologies. Aspen Compressor, a U.S. company made in U.S. that has just some really nifty technology. And it's hard to get refrigeration components in low quantities.
Oh.
Most of these companies...
They don't sell to consumers or individuals.
Not only do they not sell to consumers or individuals, but if you go to an HVAC store, you're not going to find compressors like this. You're not going to find components like this.
Right.
They sell repair parts at those HVAC stores. So it's difficult to build the supply chain knowledge to know where to get this stuff. These two components are US made. This is a heat exchanger from a company called All Coil, which is in York, Pennsylvania. And they make small quantity components great for specialty applications like what we're doing. If I was to go to a company, say in China or Thailand, that makes these for refrigerators or air conditioners, the minimum order is going to be 10,000 units.
Right.
Before they even answer the phone for you, you have to send them a check for 10,000 units, and then they'll talk.
Right.
All Coil is great because you can order one.
Oh, and to be clear about the structure of this is just a wide, flat tube.
Yep.
And through which the material passes, and all of this are simply surface area
That is
of
all
the
surface
aluminum
area.
meant
Correct.
to shed the heat.
Correct.
Okay. That is super cool.
So this is called a microchannel heat exchanger, and it has literal microchannels that run along the length of each of these serpentines. So there's maybe 100 channels from top to bottom here, and we push gas in this end. The gas flows through.
And because we're pulling so much heat out, the gas is a liquid by the time it comes
Correct.
out the other side.
Correct.
That is freaking cool. That is really, really nifty. And you can see all the way through this thing.
And the larger the heat exchanger for a given amount of gas that we're trying to cool, the more surface area we have to cool that gas, and the less air that we need to blow over any given surface.
Got it.
So the bulk airflow could be the same, but if the bigger fan I make for a given amount of airflow, the slower and quieter the fan can get. So if I have a really tiny fan and I'm blowing, say,
X number of CFM,
X number of CFM, I have high velocity and it's loud.
Right, right.
If I double the size, I quadruple that surface area, and I can reduce the velocity proportionally,
Right.
and then also have quieter fan blades because they're not slicing through the air quite as fast.
Oh, okay. So the bigger fan means that it's quieter.
Right.
Okay.
It also means that we can really crank your system up if you want. If you're like, I need 800 watts of cooling, good things to know about the body. As we're standing here right now, we're not being very active, we're dissipating about 100 watts of heat. So you think about
okay.
a hot light bulb, those incandescent light bulbs. I guess the kids might not know about those.
Yeah, so when we were kids, the brightest light bulb was 100 watts, and it got really hot.
It got really hot. So,
and that's what we're putting out kind of the same amount of heat
over our entire
bodies.
Correct.
Okay, so it's much more room temperature.
This compressor can pull out a couple thousand watts.
Really?
If you crank it up to the max.
Wow.
So we're not going to need to do that to keep you cold, but if you decide that you want to sprint through Comic-Con, you can
doesn't?
just crank the knob up and get more cold.
Amazing. Okay, I'm getting really psyched about this.
So we got our compressor, we got the heat exchanger that we're going to get rid of the heat with, and we're going to position this above the compressor.
Okay.
We have a heat exchanger that we're going to boil the refrigerant in, and I brought two options here, and I think we're going to use the larger option for you for several reasons. One is this is called a brazed plate heat exchanger.
Wow.
And it's stainless steel. We put refrigerant in these tubes, through those tubes, and water through those tubes.
Oh, and they don't
channels.
mix.
Correct.
But they exchange heat between the two.
Yep.
Freaking cool.
And we can attach some fittings to this end, which let us blow water through here and then into your suit.
Wow. That
And
looks
then
like
we're
an
gonna-
NPT.
It's actually
not.
It's a British straight pipe thread. And the reason why British straight pipe threads are used for these is
Instead of a tapered American NPT. Okay.
So the taper thread is basically a compression, stretching, friction fit. So you're literally stretching the metal as you tighten that down. And that's great, except once you've got that preload, you have to maintain the preload or else the fitting fails. And if you're heating and cooling and heating and cooling and doing this thermal
by
cycling,
definition putting a lot of movement into the system, and it's going to work itself away.
And it works itself loose. And no matter how much thread lock you put in that, eventually it will work itself loose.
That's amazing. In my book, when I was writing the chapter on glue, that was one of the hardest parts to write. Was you've got to think about what the glue's going to go through.
Yes.
And it's expanding and cooling. That means it's going to work itself away from this or that material if it's not the same material property.
Exactly. Exactly it.
Very cool.
We use a straight thread, and then the seal is created with a gasket.
Oh.
And that gasket just provides a little bit of preload, and if the gasket ever, maybe 10 years from now, the rubber hardens, you unscrew it, pop in another one, good to go.
All right, I like this. This is great.
So we hook these components up with some copper tube, and the one piece that's missing here, we use the compressor to put work into the system, and then we exchange heat with this first heat exchanger.
Yeah.
Now we have to create some way to reduce the pressure. So we keep the high pressure side high pressure. We have to drop the pressure so that the refrigerant will boil.
Right.
Since we have liquid coming out of the bottom of this heat exchanger, we want to boil that liquid off. And if you think about water in space, the vacuum of space is a low enough pressure that water will just boil off, and as it does, it will absorb heat.
Right.
This is the same thing. We have a pressure low enough that this substance here, which is our refrigerant, will boil at the pressures on the low pressure side of the system.
And this is a new kind of refrigerant that doesn't add to the ozone hole that's rapidly closing like Freon used to.
Yep.
Okay.
So this was developed as a replacement to Freon in the early 90s and does not destroy the ozone layer.
And not many people know, but among human beings' many crimes, the ozone hole is about to become an ex-human crime. It's been closing steadily over the past 20 years as industry has responded.
Yep, and very occasionally we see blips of
rising
where factories in China, I think there was a recent story.
I think I heard that. I heard Amazon and fires also helped contribute to the,
So,
so how do we create that low pressure system?
So we create that low pressure system with the copper tubing equivalent of a resistor. It's basically just a flow resistance that you can either use a small nozzle to create that pressure drop. So you have high pressure behind the nozzle and you have low pressure in front of the nozzle. Or we can use a long length of copper tubing. So any length of pipe will create resistance and friction as the fluid flows through it.
And it literally operates exactly like a resistor, which does it with electrons, but this does it with fluid.
Exactly.
So the whole analogy of electrons to water pressure actually still works. It still tracks.
Yeah. Yep.
That's great.
The copper tubing we'll use, the length is going to create the pressure drop, and we can change that length to change the pressure drop, and that's going to have an effect on the temperatures that you'll feel.
Great.
So we're going to pick something that will give us a little bit below freezing for you at a high speed setting of the compressor.
Terrific. I'm going to action getting us some vodka in the shop, and I also have a new cool shirt that's actually a full body cool suit. And that's the one I want to try. I bought it's actually a 1980s British RAF cool suit for high altitude flyers, but the tubing all feels like it's good. It's still like extant and flexible.
Excellent, excellent.
Awesome. While you gathered that, I'm going to get those brought in. Right? Right?
That's excellent. And the tubing is perfect.
Feel it. It's way tinier than I thought.
Oh, yeah. Yeah, that's great.
So there's some big ones that run out. I haven't pressurized this, but my cursory inspection led me to believe that it is in pretty good shape. Yeah, this is expensive. And the tubing, it's funny because this is the other question I have is, there must be optimizations you can make for flat tubing that has a greater skin contact and thus a better heat exchange.
So there is. The funny thing, there was a discovery in the early 2000s from some researchers at Stanford, Dennis Gran being one of them, that you get the best heat exchange through the parts of your body that don't have hair on them. So your palms, soles of your feet, your face, and you can do more heat exchange through those surfaces than by putting a suit around your whole body.
Oh my God.
But I think putting the suit on your whole body creates perceived comfort in addition to some actual heat exchange. And that's really important too. There are a couple water pump options.
Oh, look at that.
And this is, gotta have a water tank.
That's the size that you need? It doesn't need to be bigger than that?
Doesn't need to be bigger than that. So this is the exact size that's in the high seas suit.
Wow. And this is a different one.
This is a different one that's a tank and pump built in.
Ooh, that's kind of sexy too.
So I figured you might appreciate that.
Oh my gosh. This is amazing. Since as an engineer, I appreciate less complexity equals more reliability. So I'm inclined to go with the pump reservoir combo. What do you think?
We should try them both out. The nice thing is we can build the refrigeration circuit,
right,
and have that be a standalone thing, and then you can play around with different options all day long. So
great.
I have in the CAD right there. There's a little pump that is right here. Mm-hmm. This is this amazing British $200, really high quality, high pressure, super quiet water pump. And I didn't get a chance to grab it because I was running late to the airport. So I was like, oh, well, we'll just use the one that I shipped.
This is great. This looks like a kind of almost like a vape pen.
Yeah. We need some LEDs in there.
Yeah, exactly. Boop, 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 boop. Okay, so what is the first step for assembly?
So really the first step for assembly is we want to set the components up. So we've got 2 heat exchangers that we're going to need to basically position and then braze some copper tubing into.
Okay.
And if we go with the drawings that I've made, I think the ideal setup is going to be something along the lines of this.
Okay, so do you need me to make a bracket?
So we can make a bracket, or I think the process that I usually use to do this is positioning the parts, and then figuring out what the copper tubing run should be. And we've got the high seas model that we're starting with, but we're going to use a different heat exchanger than I use with high seas. So the high seas system used this heat exchanger, which I haven't talked about yet. Okay. We should talk about that for a second.
Okay. What's different between this heat exchanger and this one? It's same thing, 2 different channels for different liquids that are kept opposed to each other, yes?
Yep. And this heat exchanger is a stack of steel plates with some ridges on them, and those steel plates are pressed together, put in a furnace, and then the furnace brazes.
Almost like surface mount electronics.
Almost exactly.
Okay.
And that stack, you can see these kind of formed channels, and the way this bottom plate is a pan, all the rest of these plates have that same pan feature. Okay. And so you stack all the pans up, and the pans alternate refrigerant, water, refrigerant, water, refrigerant, water. The brazing process is you could do this with a torch, but doing it in a furnace gives you good uniformity. This heat exchanger is also steel plates, but these are flat steel plates, and they've been
etched out of them?
The channels have been etched. So those plates are thin enough that we can use etching processes, and this is then vacuum furnace bonded. And the bonding process involves heating up, you put a dissimilar metal bracket around it, and that similar bracket, when you heat this, the steel expands more than the bracket does. So as the steel is expanding, the bracket creates a compressive force that diffusion bonds the layers of steel together.
Good God, wow.
So we can etch microchannels in using photolithography processes that are super precise. We get a much smaller, more compact unit that doesn't quite have the capacity of this, but you can see is
that's an impressively small thing as a heat exchanger for something that can cool down a human body.
This is rated at 800 watts of cooling.
That's unbelievable.
This is rated about 1.2 kilowatts of cooling.
And this is so efficient because you can get high amounts of precision in the etching process, and thus a lot of flow through it, even though it's really tiny.
A lot of flow and a lot of surface area for exchange.
Right. So surface area is everything.
Surface area is everything. And the difference in price of these is also pretty funny. This is maybe $40, $50, get them made in a factory overseas. This is about $400. So it's a 10x difference in cost.
Okay, I see.
Super cool technology.
For one-off projects, those aren't crazy price points, but
No.
for any business venture, that is a
Right.
giant difference.
You really have to have a need for using something that size. We're going to use this mostly because we can put threaded fittings on
Right.
and make it really easy to interface directly with your suit and pump.
And when you're holding this up here, and this goes with this,
Yep.
I would love to know if these pipes can be. While I have a lot of room to put in, let's say, a fake pliss
Yes.
for a spacesuit, this space will be a premium. So
Yeah.
I'd love to keep that dimension, this X dimension, as narrow as possible. So I'm
Absolutely.
assuming we can cut these a little bit tighter.
We're not going to cut them, we're going to bend them.
Oh, okay, great.
So
I've got some metal benders
Perfect.
too, and some flange tools should we need those.
we'll
and
bend
yeah.
the copper tubes around so it'll create a nice flat profile.
Okay.
We'll keep everything in a line, and that way we can get our refrigerant out to our heat exchanger. So we go out of the compressor and we go up to the top tube
Okay.
of the heat exchanger. That way, as
Okay.
the gas works its way back and forth and gets to condense down to a liquid, the liquid drops to the bottom.
Okay.
And then the bottom comes out and then goes to the bottom of this heat exchanger.
Okay.
Where we boil up. So we end up with the gas at the top.
Okay.
And then that
Oh,
gas
right.
gets...
So there's a direction to this.
There is a direction to
Okay.
this. Yeah.
And then to mount this to this, I'm assuming we need a little bit of some bracketage. Is that
Well,
correct?
Brackets will be good. We can zip tie it, but brackets are going to be better.
Okay.
So ultimately,
I have
once-
endless numbers of spacers and
Perfect.
little nuts and bolts, and even all thread should we need it.
After we get everything positioned the way we want, we'll mount it on a fixture.
Great.
80-20, a piece of wood, just so that we can braze it.
Yeah.
Once it's brazed, it'll hold itself together,
Okay.
and then we can make sure to measure and create a bracket that holds everything into your suit.
Fabulous.
Don't put any strain on
The joint.
the aluminum to copper joint, because aluminum copper joints, there we go,
They're delicate.
are very delicate.
Oh, that's lovely.
Yeah, it's soft, and I can guarantee that I'm not overloading the joint.
Right.
Notice that it stays straight as it comes out of here. And I
Right.
got most of the bend.
And that's important because we didn't stress
Exactly,
that at all.
Exactly, because
Okay.
if we lose these connections, brazing copper to aluminum is one of the hardest things I've ever tried to do.
Don't want to think about it. Don't even want to think about
Haven't
it.
succeeded. Better people than me can braze those joints.
All right.
I'm gonna have a tube that's gonna come out of the compressor and it's gonna need to get into here.
Right.
So
So-
if I flip it like that,
And then it comes in the top.
I can come out and
Yep.
then up in the top.
Okay. That seems great.
So that makes that easy.
Okay.
And then the tube that comes out of the bottom is going to go into our expansion valve. So we're gonna have something like this come in here. We'll have a coil of some of this, and like I said, the length will determine the temperature. The determinants of the temperature are the length of this tube, which gives us the pressure drop.
Okay.
The speed of the compressor, which tells us how much gas we're moving, how much mass of refrigerant.
Past a
we're-
certain point, right?
And then the amount of refrigerant that we have in the system. So we want to balance those three things, and we've got some tools to do that.
Okay. How do we braze this to this? Does that get brazed or is it a pressure fit?
That's going to be brazed. We're going to braze all this stuff together.
So do we need to machine some specific copper little couplers?
Yeah, we could machine them, or we could just take a pair of pliers and crimp the soft copper tubing down around this. Which
Oh,
is
really?
the way- yeah.
And that's doable.
And then you just fill some
Amazing.
brazing material in the end.
You know that I do. I just want you to see the glory that I did invest in a full retail rack of both of these. But I'm all about the simplest possible solution. Just know that I have.
Oh, this is good to know. One of the funny things about this tubing, you saw how easy it was for me to bend by hand
Yeah.
there are two styles of copper tubing for refrigeration. There's drawn tube and then there's annealed tube.
Right.
The drawn tube is pretty rigid.
Right, because it's been mechanically drawn, which means it's work hardened.
Work hardened.
Yeah.
The annealed tube, after you draw it,
It's been baked, so the steel is
release all of those
tensions of the crystalline structure
Exactly.
inside. Yes.
And it's super bendable, and it's really fun to work with.
So you don't need college to talk engineering.
We should not mention how many degrees I have.
I have zero. I have honorary degrees, which are worth just as they're worth nothing, actually.
Believe it or not, I think that the out-of-school education for me has been so much more informative. So my background is biomechanical engineering.
Right.
This is all thermodynamics. And what's really, really fun about this is, yeah, I'll make fun of my education. It's a fantastic education, and it has served me extremely well. But when I took thermodynamics in college, I couldn't tell you what all these parts were, how they worked, what they did. I could just tell you the math behind what they were supposed to be doing.
Right.
And the gap between that theoretical knowledge and then understanding not just like why do we have a capillary tube, but what these parts are, how you put them together, that gap was pretty big. In closing that gap, not only did I take that theoretical knowledge and then the practical knowledge and bridge it, but it gave me a very deep appreciation for how these systems work and how you optimize them and how they behave. And I think that that's something special that we really need to get more engineers learning the practical side so they see that, and get more of the technicians understanding a little bit more of the science.
On Mythbusters, we frequently had trouble when we'd call up one of the world's experts in the field we were trying to explicate, because they'd be so much of an expert at the one thing they knew, but they couldn't discuss with us how it cross-correlated to this other part of the story. And nothing exists within its own frame. It's all reaching out to deal with other frames. And so we found the polymaths, the people with more wide ranges of experience, much more able to talk to, speak to, and adjust between multiple fields.
It's amazing the contexts that connect something like this and how much knowledge of this context really, really helps put those pieces together. Like, okay, I see a compressor, I know what it does, and then I know the physics of what's happening, so I understand what goes on inside this heat exchanger and what changes when I speed the compressor up or slow it down, or change the diameter of the capillary tube, or change refrigerants from, say, R134A, which is a Freon. It's not
basically every
Freon
change affects multiple other systems. And so it's not just as simple of move this and this happens. It's all these cascading effects.
I can change the chemistry of the refrigerant, and that changes everything else in the system.
Wow.
And understanding what those effects are, or change the speed of the fan and what's going to happen. How much liquid refrigerant do I have left over when the speed of the fan goes up?
Amazing.
All those things are connected.
Well, I figure it doesn't matter how far it goes in, right?
No.
Okay, so then the bend comes about here.
Yeah, you could start bending there, and because we're just going to want to clear the fan.
And I'll stay in line with the, I see, I kind of want to be in line with that valve at the bottom.
Yep.
Oh, I love how soft copper is.
This is the best stuff to work with.
So then, once we have that, and I think I can actually come in even tighter. Yep. And then this comes around here and comes that way. Wow, it looks like I actually cut it almost the perfect size.
I think you cut it just about the perfect size.
Wow.
And even if you didn't, we could fudge it a little bit, because we're going to do the same thing. We're going to insert this into the mouth of the compressor, since it's a 1/4 inch. Don't pull that out just yet.
Okay.
So the reason why this has the plugs in it is that the compressor has an oil that's a polyoether oil, and that oil absorbs moisture. And as it absorbs moisture, it creates an acid, and that acid over time will eat away at the insides of the components. So we don't want to.
So I'm going to cut this down by 1/2 inch because we don't need more than that, and that'll allow me to go in just a little bit farther.
Oh yeah. If you want to,
Yeah.
And how much copper to steel brazing experience do you have?
Some.
I'll do the first one.
I'll tell you the stuff that I use for everything is Stay Bright silver solder.
So I'll grab Stay Still 56 or Safety Seal 56, which is a high silver content phosphorus bronze brazing rod.
The high silver is we always use it in special effects because it's strong.
It's really strong, and it's just about the only really sensible way to create the copper to stainless steel bond.
And I was doing it to what did I buy? Oh, those stainless steel chrome. Those are brass and then chromed balls, and I'm able to braze brass to them.
Nice.
Right through the chrome. Yeah, it's really nice.
That is pretty awesome. So we'll do that to copper to stainless here, and so we've got that connection. I think that's going to look nice.
Yeah.
the bottom of this is going to come out, and we're going to go into the capillary tube, and we'll basically spiral this down and come into the bottom of the heat exchanger here. So we're going to take a little 1/4-inch pipe and make a straight stub to come out, and we'll crimp that stub. We'll crimp this into here.
All right.
And we'll crimp a stub into here.
So we're kind of, what we're doing right now is setting up all the brazing we're going to need to do.
If we don't do a great job cleaning the copper tubing, those little copper filings will flow through the system and end up in the compressor. We don't want that to happen. So we use this filter dryer, which has a little filter on the inside. And I've had these made at a factory, custom built for me, so that it's got the right diameter to slip right on there, and for our capillary tube to slip right in there. If we didn't have that, then we'd have to create fittings that make all these things go together. So this will make it a lot easier. Perfect.
And it's fully cleaned out with a 3/16 reamer.
Excellent. So this, Adam, is, I brought a couple filter dryers because I didn't remember which size we're going to need. But this has a perfect fitting to slip right on there. And then we're going to slip that in here.
Sexy.
And we're going to have a maybe 30 to 32 inches of tube coiled that will go from this point here down to this point here.
Okay.
Yeah, the really nice thing about that bender that you have is you can do clean 180 degrees.
Yes. That's nice.
Yeah.
Okay, so then
we're just going to do 180.
Almost a full bend.
Yep.
From right about here?
Yep.
No copper dust in there. So.
Perfect.
Look at that. Right there. Okay, so then that goes there.
Yep. So that's it. Those are the pieces.
Really?
Yeah.
Oh wait, but then there's this that goes to the.
Yeah. So we'll like I said, we'll have this. This one's gonna go here.
Yep.
And then the coil's gonna come out. See how this is so nicely sized to fit
really,
that?
really sexy.
It's the only thing that we're gonna do that's gonna be tricky is, and by tricky I mean slick and also difficult.
Great.
Is we need a fitting to be able to add refrigerant and a fitting so that we can measure the performance of the system.
Okay.
So
Does that mean we need a little T of copper?
you know, we could use a T of copper, but what I've found is that we can cheat a little bit and we can drill a hole into the side of the copper tube, and then we're gonna braze this in. And what that ends up looking like, so this joint is kind of
that's great.
crazy.
Yeah, we can do that.
I did this way closer to the copper.
Yeah.
So we're not gonna do it that close to the
No,
copper
no.
because I think I probably got lucky there. Just a little bit of an angle.
There's no reason to expect accuracy from drilled holes on a mill.
So having center drilled that, we have a really clean hole now.
That's lovely.
Get a nice fit there. Oh yeah.
Oh, good.
One thing, it's really important to always remember to take your Schrader cores out before brazing.
Brazing, yes, because the O-rings will melt
otherwise-
and that makes things bad.
The decision is always, we can flux this or not.
Really?
If we're doing copper to copper and it's fresh, clean copper like this, flux is optional.
Oh, I didn't realize that.
We got a little bit of an orange tail. I want to try to get that to be a little bit. Okay, that's pretty good. Yeah, it's a nice little. All right, so we'll keep that joint clean. it's really important to flux this joint because we've got the dissimilar metals coming together, and the flux is what's going to allow the brazing material to flow in between the metals effectively. So we want to get good coverage on the surfaces, and it's going to make all the difference. So that should fill that material up. We'll clean that up to make sure we got our good flux coverage again. And then we're gonna heat this sucker up. The secret here is we want to heat up the copper first and the stainless steel last.
How's it going?
Oh, you're here just for the right part. So this is the copper to stainless brazing.
And this is a tough thing, yes?
This is the tough thing. So we heat up the copper because the copper conducts heat a lot
incredibly
better.
well.
And it's just gonna pull the heat I give away.
Right.
And I'm just gonna keep stroking the copper with until it flows.
And then it's wetting.
Then I can just get the stainless a little bit. Make sure we get good coverage.
Dude.
And we got a really nice, clean joint.
That's awesome.
You can see how uniform that.
So you're actually feeding nitrogen in here while you're doing it?
Yep.
And we shut that down now?
You can leave that on because I actually filled this with nitrogen, and since nitrogen's heavier than the air. I filled it with nitrogen, I backed off and it just sits there.
Very cool.
So that's one joint. And the other thing I'm gonna do is, this right here. Now that we've made that joint, I want to make sure that we flow through here.
Yeah.
Because if I screw it up, that's never good. So we should get a puff. There we go.
Oh, because you'd see it step out there.
Yeah, so if I fed too much brazing material, it'll clog it up. I've done that once out of about 150 systems, and it's like, let's never do that again.
And so now you're going to do the same thing again with this one?
Yep.
All right. It's always terrifying brazing stuff near other stuff that's been brazed.
Yeah, yep. Fortunately...
Oh, I see. You needed the goggles, the shielding.
Yeah, I mean, it's really not that hot of a flame, but...
yeah, no, it's good practice, because the oxy rig will make you blind for a day if you don't pay attention.
All right. That looks good. So it should be really uniform. Some of that is definitely flux. It's always good to clean the flux off and make sure that that's...
Do you need a specific chemical to do that?
You need dihydrooxygen. Yeah.
Okay, I think I've got some of that on tap.
Yeah, so that's the stainless to copper, and we can take advantage of these fittings once they're brazed in to fill the system with nitrogen as we go along. So we're gonna have this sitting here. We'll pop that into the compressor.
And I made this slightly long in case.
Yeah, well, instead of cutting it, I just bend it up a little bit because it's so much easier.
Right.
Once we
you
can
just roll it.
Yeah, we can roll it. We can work with this straight piece here. So we're at that point where we can look at the last couple steps. I always do the compressor last, partly because the compressor has the oil in it, but also because we can get everything else set up, and if anything has to get tweaked, we can tweak it, and then the compressor will be the last joint to make.
Okay, so there.
The next joint we can do, if you want to rest that tube on top of the compressor.
Yep.
The next joint we'll do is the coming out of here and then going down into here. It is still
and we just dunk it in a glass of water, right?
Exactly. Get all that water right back in there.
Is it hygroscopic? Will it pull water back in as it cools?
Yeah.
Okay, so we want to get it up quickly.
So we'll hook it up while we're still pretty warm, and I'm doing all the brazing with the high silver content material just because we can, and it'll look pretty once it's all cleaned up.
There's just a little in the back.
Oh yeah, thank you.
So I'm just gonna make sure it's got coverage.
Good.
Great.
Slide that puppy on here.
Aww.
And then we want to measure out. I could do these separately, but we'll do them at the same time.
Okay.
So got stay silv. Why the heck not use that as the spool?
Nice. Oh, can I do this part? That looks really fun. I
is
love
really
this
fun.
kind of thing. Thank you for letting me have
Leave
the
like
fun part.
4 inches off the end. We can spool it and unspool it. It's
Yep.
super soft. That's perfect.
Oh, whoops.
Oh yeah, sorry. I should probably close that first.
There you go.
Excellent. So we're gonna stick this in here, give it a little Scotch-Brite, and then once we get everything set up, the last thing we'll do is unspool it, insert it in there, and close everything up.
I guess it's just a straight up tube filled with desiccant, right?
Yep. And there's a little mechanical filter, strainer filter on it as well.
So you're not doing anything but just improving the desiccant by getting it hot.
Right, right.
Nice wetting.
So get that good wetting. Make sure there's lots of extra in there. Sorry, try to avoid getting you.
That's all right. I can take it.
All right. And then one of the things, again, I'll do is make sure that I've got good flow and I didn't plug any holes. So I'm gonna hold my finger over that.
Yep.
And then, yeah, feel that.
Oh, yeah. Oh, nice.
Yep.
Now, careful about breathing in that nitrogen.
Yeah.
I'm kidding. It's just an asphyxiant, right?
That's exactly it. So we're in pretty good shape. The final 3 joints to do, I think we'll do the compressor now, and then the last one we'll do is this.
Okay, so
now we actually want to pop out the plugs. And the faster we do this one, the better. Works. That's perfect.
That was it. Okay.
It's just a little bit of cleaning there. And then this one we'll take and we'll sneak it around like that. Or maybe we'll sneak it underneath. Like that.
And that goes in
That'll
there.
go there.
And
So
do you want to put some...
Scotch-Brite that.
Yep.
These are the other 2 tricky joints because heating up a painted compressor.
Right.
With oil in it.
Yes.
It always is fun.
And okay, that's as deep as that one's going.
Yeah. So again, we could just do regular
because it's so clean.
because it's clean and it's copper to copper, but I think you'll enjoy the shiny silver finish of all the brazed joints. So now there's a fun bit where we can put pressure through here. We should get something out of here, and then I'll put my finger on here.
Yeah.
And then that will pressurize.
Come out here?
Yep. See, hear that? The little click in the compressor?
I'm hearing something leaking somewhere.
Yeah, that leak is right here.
Oh, that's that.
Yep.
That's
so
what
if I
that
put
is.
my finger here,
Oh.
this tells me we have a complete circuit.
Wait.
So
yeah, that's awesome.
we've got pressure all the way back through our evaporator, the cold side.
Yep.
We've got pressure through the compressor, and we're actually pushing nitrogen through the compressor, through this heat exchanger, through the filter dryer, and then out the capillary tube, which we will then hook up to here. This is the last brazed connection we have to make, and then you have a fully completed circuit. We'll put that in a bucket of water.
Yep.
We'll pressurize it with nitrogen, make sure there are no bubbles,
Okay.
and then we know we have a sealed system we can pull a vacuum on.
Incredible. And then this is where the water circulates through.
Yep.
This is the business end.
That's the business end. So electricity in here, cold out of here. At this point, everything is ready to go. So all we got to do is bend this down, insert it in here, and we use the pipe cleaner also
just to make sure
to
it's clean.
clean out any oxidation. Since we've done all the brazing under dry nitrogen, it keeps the dryness, makes sure that we don't get any water in the system, any water in the oil. The nitrogen part is nice because we can get it inexpensively.
It prevents any heat oxidation inside during the brazing.
It prevents the heat oxidation from causing like this kind of flaking you see on the outside.
Yeah. Oh, that would end up compromising the flow.
Right. That ends up inside.
Right.
And that material, the oxidized copper, just clogs the oil. And over time, it might take 10 years, it might take 1 year, but over time, if you got enough of it, it can cause the system to fail.
Unroll it like this, and then do a kind of a twisty twist.
Yeah, nice.
And have it come down like that.
Exactly.
And then it just would sit like that. To me is kind of nice.
Perfect.
That seems like cheating.
It is. So I have got a little bit of motion, so I know that I didn't crimp down on the tube itself. So I just close this off, and if you look at the end, there's enough of a gap there. All I got to do is fill that with brazing material, and then we're good. So this is a pretty easy joint because there's not a lot of copper here. And we just fill in the end just like that, get it nice and silvery.
Amazing. So fast.
That is done. We have a fully built system now. Should be all done with the brazing part. And we're ready to leak test.
It's time to leak test?
It's time to leak test.
Okay, so now you need a bucket.
We need a bucket of water.
All right, Kipp, this is what happens when you ask a science communicator for a bucket. It's what we can see inside of. That should hold the whole thing. I think we're gonna have a little displacement. I may need to add a little on top.
I don't want to get any water in the Schraders because that water can then potentially get entrained in the system. So I close these, we have a nice gasket on the inside.
Oh, nice.
And actually I'll use this one to fill. So we take our nitrogen, dry nitrogen, attach that, we've got our Schraders in now, and we'll do a pressurized bubble leak test.
Okay.
Where...
Oh, I see. We'll pressurize it and put it in to see if it's coming out anywhere.
So we're now at 200 psi of nitrogen.
May I?
Not yet. Before we do that.
I got excited.
It's good to get excited. It's very important. We're going to disconnect this line.
Oh, so now it's still under pressure.
So it's still under pressure. We have
because of the Schrader.
Exactly. And this is why having the Schraders in, number one, I know that I have the Schrader in now because I pressurized it. We do this, and if there
That's coming out of the...
That's coming out of there, yeah. Interesting. I think that's a leak in the heat exchanger itself.
That is a leak in the heat exchanger.
Yeah, that's a pinhole heat exchanger leak. Well, all of my braze joints are good.
Do you want to try and braze that one shut?
I think we should try to braze that shut.
Okay. Ooh, that looks good. Damn. All right.
Okay. Let's cross our fingers and hope that
we didn't add 5 new leaks.
Right. These are loss-free fittings or low-loss fittings.
Amazing. I was amazed when I found out you could do that by using hydraulic quick connects with pneumatic systems.
Yeah. Yep. All right, I just put it up to about 300 psi, so really will.
We should see something immediately.
If I did a good job. Yes!
Ha!
I've never done that before. First time ever. Wow.
Dude, that was an awesome fix. Now I just want to make sure we get all of this underwater.
Let me put this cap on first.
Oh, yeah.
There we go.
Sorry, thank you.
No worries, thank you. Perfect.
And I see no leaks coming from anywhere.
Yeah. Amazing.
Dude, that's
nuts.
Our day could have gone any which way, right? This video could have been the first part of a video that's weeks long in the making, or we're done by the end of the day. That is awesome. So do we leave that in there for a while?
No, we're good. We have a leak-free system.
Leak test done.
That is the leak test done. You have a hermetically sealed system as far as we know.
Oh my gosh.
And the next two steps, we'll pull a vacuum to remove all the nitrogen.
Okay.
And we will...
Oh, and then we fill it with the thing.
And we fill it with refrigerant, and we've got that. So we'll pull a vacuum to remove the remove the nitrogen. We will fill it with a little refrigerant, hook up the electronics, fill it with more refrigerant while it's running, and then you'll have a perfect system.
Amazing.
Inside my gauge set right now, I've got a very high vacuum that I pulled over the weekend. And we've hooked up a can of automotive R134, which is the refrigerant we're going to use for this.
And you have to be certified
to
plumb this, is that correct?
Yes, so I have
certified
a
HVAC.
universal EPA HVAC certification. Under normal circumstances, we would use in any real HVAC work a 30 kilogram tank.
Like a big bottle.
Or a 15 kilogram tank.
Right.
You know, big bottle. In the case of a system like this, we're really only going to put about 30 grams, 40 grams of refrigerant in.
Okay.
So it doesn't make sense to have 15 kilograms when we only need 30 grams. As an alternative, this little tank of refrigerant here for automotive purposes is 340 grams. So we'll end up using 20% of this bottle instead of like 2% of a really big bottle.
Oh, that's awesome.
We've had to make a little jury rig connector to get from the automotive bottle and the automotive can tap through to our standard refrigeration fill line. And we brazed that in the other time. So I've purged any air out of my refrigeration line and we're ready to fill this. So we always fill the suction side, which means adding refrigerant to the blue line.
Okay.
And to do that, I'm going to make sure, I always start off making sure my valves are closed. This one I can have open because we're going to add refrigerant here. We've zeroed out our scale. I want to know how many grams we put in.
Okay.
It's helpful to understand how the system's behaving. And at this point, it's pretty simple. We open this up. We open this up, and we're going to squeeze the trigger to add more refrigerant. So we've now added a starting refrigeration charge of, let's see how many grams we've got. 3 whole grams of refrigerant. So we've got about 3 grams in the system. The pressure has gone from high vacuum up to 55 PSI. And this is when we can start the compressor. Since we no longer have the system under vacuum, we have some minimal refrigerant charge in the system. We can spin the compressor and it can do some work. Once we get the compressor moving, we'll continue to add refrigerant until we see a couple different values appear on here. So I'm going to grab 2 other clamps so we can watch the temperatures.
Oh, amazing.
So this first clamp I'm putting on the suction side of the compressor.
Okay.
And what this is going to tell me, this is really fundamental measurement. We're going to be boiling refrigerant off here, and the refrigerant's going to come through this heat exchanger. And as it's absorbing heat, we can measure the temperature when it gets to here.
Okay.
We're also measuring the pressure at this point. So at a given pressure, we're going to have a given boiling point, given temperature. For water, water boils at 100 degrees. The steam that's generated can be hotter than 100 degrees. The water itself can never be hotter than 100 degrees Celsius, 212 Fahrenheit at sea level. But we can change the pressure. Like if you go to Colorado, you're at a higher elevation, which means you're going to have a different boiling point and different temperature. So we can modulate those boiling points by changing the amount of refrigerant in the system and changing the speed of the compressor.
Fascinating.
So we're gonna,
and that can change overall how fast it can go through cooling cycles and how much it can cool.
And also how efficient the system is.
I never realized it was an adjustable set of values within that. I just thought you put it under pressure and boiled it off, and in that exchange, you got cold. But you're with
part of it.
Different pressures yield. Right. Oh my God.
So we can adjust those pressures and temperatures, and we're going to adjust them to make the system really efficient and also give you the right amount of cooling.
Amazing. Because there's an optimal relationship between the values.
Exactly.
Is that the case?
That's exactly the case. So
I'm
going to go ahead and make sure this is all ready. And if you feel this, actually,
It's already probably getting a little cold.
that should be cold. These cans are not the best. These fittings leak a little bit, so
I see.
I want to make sure that keep our pressure up here. And now we can basically spin the compressor. Now, this control board is ready to go, but I'm going to take a little shortcut here, which is...
You're going to wire right to the compressor?
We can wire right to the compressor. I'm hoping that my software is still running on our little Arduino board, but we're going to plug in 24 volts. Hook up
Do you want me to turn this off?
grounds. No, go ahead. I don't mind plugging things in while they're on. It's all low voltage.
Yeah.
Nothing to be afraid of here.
Bzzzt.
All right. So give that a second. We'll see if that turns on. And if it doesn't, then we should wire directly in.
Whoa!
There it goes.
So that was a little
right.
check system
Yep.
that it was going through to make sure it was finding everything it wanted to find?
Exactly. And now that the compressor's running, I'm going to keep adding refrigerant.
Okay.
And I'm going to watch these temperatures. So this is the temperature that we're boiling at.
All right.
So I want the warm side of this to be warm enough that we can reject heat, and the cold side cold enough that we can absorb heat.
Right. This is getting warmer.
Excellent. And if you
Oh,
feel
that's definitely getting colder.
right down at the bottom here, where the
Oh,
boiling is taking place, that's going to be the coldest spot. Other thing we can do is if you have another jumper, I think we're going to jump the 5 volts directly to the speed setting so that I don't have to plug my Arduino in.
Ooh.
All right. Let's sneak that in here. There we go. $77. The fan on here, we can start to get rid of some of that heat.
Okay.
Oh yeah, this is getting nice and hot on the hot side.
Okay, so now you need a third power supply.
Before, when we weren't taking the heat away, the cold side was cold, but it was not as cold as it is now. Now we're getting rid of that heat. The cold side is extremely cold to the point where we've got a layer of ice forming on all these tubes. Once we hook Adam up, we will get a load, so we'll start taking Adam's heat away into this system. And then when we crank it back up to full speed, Adam will get cold quickly.
Oh, this is incredible.
Outlet into the top one because we want to go counterflow. We want to have cold refrigerant going up, and we want to have the water going down. That way you're going to get the most effective cooling fastest.
And then it comes out of me into there. Yeah, it's pumping out a lot, isn't it? Oop. That seems like right.
Let's crank it up. We're going at slow speed here. So
I'm going to
you crank that fan.
20, that's 24.
And
24.
We're going to go.
Now we're going to 12. And you're going to do that jumper? Ooh, yeah. I was thinking it didn't feel like it was getting any colder, but now it is. I mean, I'm definitely feeling cooling all over. I love that this 1975 Royal Air Force cool suit, still totally functional.
See how fast we can go before you kill the
I'm feeling
pump?
it. Like the moment you did that, I'm feeling a difference.
Yeah,
that seems to be one of the limiting factors in how cold we can get.
Yep. Yeah, I can feel the difference here too.
Because we're circulating. So we definitely need a more powerful pump.
Yeah.
Dude, check me out. I'm getting cold. This is the most elaborate way to get cold. In most of the United States right now, you just walk outside. This is also helping it sink in how incredible it is that NASA built this all into their spacesuits, right?
Absolutely.
So like everything here is in a self-contained spacesuit along with oxygen and other stuff going on and other telemetry. I get it. I always understood how the system worked, but seeing its level of complexity is kind of amazing.
In the vacuum of space, dealing with temperature is really tricky because you can't conduct temperature away by having air that's cold or hot.
Right.
You've got solar radiation that's bringing a lot of energy onto people, and then you're giving away photons out in space. So there's these trade-offs of heat flux. NASA had a system that kept astronauts cool by actually boiling off a gas into space, or boiling off a liquid into space, and basically just vaporizing it. And as you do that, you can have a lot of phase changes happening here. That phase change absorbs energy, absorbs heat, and ta-da, you're managing temperature.
Now I feel like I'm standing outside on a 40-degree day. I'm starting to get real cold.
It is actually, I think we're hitting some good set points.
Take a look at the thermal image.
Oh yeah, that's awesome. Yeah, you can see the lines on your body where the FLIR is picking up all the cold tubes. That's spectacular.
I think that's what I would call a successful test of the mini refrigerator that Kipp designed and we built here because it has me freezing and I want to say cut so we can wrap and I can get on some normal street clothes. So cut!
Really noticeable.
It's moving. It's moving the heat.
Yeah, man. And if we crank up the pump, you're gonna. That's pretty awesome.